Oh, hello. I'm sitting here in New York City, looking out over the Hudson River. The sun is just going down, and I'm very happy that I'm able to do my little bit to help this. And I hope you all do what you can in this rather horrible emergency. And I'm going to talk a little bit about C++. I'm going to talk about how it came about, why it is the way it is, and as much as I can do in 25 minutes. Basically, my friend Dennis Ritchie said that there are two kinds of languages. There's the languages that are designed to solve a problem, and the languages that are designed to prove a point. C++, like C, is designed to solve a problem. And the problem had to do with distributed computing and writing code that both had to be high and low level. High level to handle the abstractions necessary for distributed computing, and low level to basically deal with the hardware, do memory managers, network drivers, process scheduler, and things like that. And that was in Murray Hill in New Jersey, in Bell Labs' research center. The top picture there is that big complex, which I could see if the hills weren't in the way. And I built on my understanding and research from and learning from my home university in Aarhus, which is the bottom left picture there, where I went to study mathematics and found that the applied mathematics I'd signed up for happened to be computer science. I was sort of confused and didn't know it had to do with computers, but once I discovered machine architecture and programming and all the rest of the stuff, I was hooked, and I've been doing it ever since, which was probably good because I wasn't as good a mathematician as I thought I was. Hey, I'm a math major. I've got a master's in it, but still, I wouldn't manage to do it for a living. And after that, I went to Cambridge because I'd gotten more interested in machine architecture, microprogramming. And on the way, I learned many languages, including BCPL for low-level stuff and Simula for high-level stuff. And basically, if you want to describe C++, you can do it in two lines. There's a direct map to hardware, which is what I learned from working with hardware, from working with BCPL, working with C. The instructions and the fundamental data types map straight into hardware, so you can use the hardware well. And we've been working on this for a long time, 40 years, basically trying to use hardware really well without getting tied down to a particular machine architecture. That was one of Dennis's brilliant moves, was that C is close to the hardware, but it's not tied to a particular architecture. But down by the hardware, it's not actually all that pleasant. Mistakes are, they're unforgiving down there. And so you need to abstract. You need to abstract from the hardware. And I had learned object-oriented programming from Christian Nygaard, who was a visiting professor in Aarhus. And so I knew about classes and inheritance and things like that. And I thought, this is the way you get away from the hardware when you need to, but you have to do it efficiently. You have to be able to afford to use your abstraction. So I came up with the notion of zero overhead abstraction. And so I took the Simula ideas and I added quite a few things and simplified a few things, getting generic programming and such. And the aim that we're almost at now is we can get type and resource safety. We can have concepts, modularity, concurrency, all of this kind of good stuff that we would like, and we're getting closer to that ideal. If you want to look at it from a history of programming languages point of view, then you can see the languages having two tracks. There's a low-level track that goes from assembler to BCPL to C, where the name of the game is to use every cycle and every byte very well. There's, of course, Dennis there in the middle, And the guy on the left is David Wheeler, who was my thesis advisor in Cambridge. And once you want to get away from the hardware, you go to the higher level there where you started with Fortran. There's Bacchus, who helped design or was the main designer of Fortran, which was the first place where people left the hardware and looked at something that was more suitable for humans, and then had a compiler that generated decent code. And that was a major breakthrough, the major breakthrough in computer science. And once the engineers and scientists had Fortran, everybody wanted one like it. And we got a whole lot of languages for special purposes, fitting special domain-specific abstractions. And this was sort of a mess because they couldn't talk to each other. And out of that came the idea from Christian Nygaard of object-oriented programming, where you basically design your own application-specific abstractions, usually called classes or class hierarchies. And I learned object-oriented programming from him, just as I learned a lot of low-level programming from Dennis and the other people at Bell Labs. And when I needed both, I sort of joined them together, and we got C++, and a lot of stuff came from there. And one thing that I'm acutely aware of, and I feel people sometimes forget, is that we are doing this for people. Programming language is a tool. It's not an end goal. The end goal is to build useful things. And I remember once in Aarhus, my hometown, where I was delivering a little program to a small business out in the suburbs. And I was sitting on a sofa with two really cute kids, chatting with them, while their mom and dad was testing out the software. And I realized if I screwed up, I would have hurt those kids. I would have hurt the family and such. And it really struck home to me that when you build something, you have to build it well. You have to make sure that it's appropriate for its perfect purpose and that it doesn't break. And basically that ordinary people want great systems. They couldn't care about programming languages. Now, software developers want great tools. And programming language is part of the great tools, but you have to remember the whole tool set. So when you look at programming, when you look at programming language, you have to think about the people that in the end will benefit or be harmed by what you're doing. And the main technique for getting away from the hardware is abstraction. You can look at anything. Here's a picture of a car. The car is made out of parts like engines and brakes and suspension and such. And in the same way, software is made out of parts, and the parts are made out of parts, etc., etc. And so you have to build these components that you can build to something major. And when you want to build something major, it has lots of parts. It has lots of things that has to be fitting together, such, and the parts communicate, and all of this kind of good stuff you have to keep in mind. It is not, the focus isn't on the individual language feature. It's what you can build from them in terms of abstraction. So let's look at an abstraction. Here's sort of a simplified vector from the C++ language, it's in the standard library. And basically we have a low-level view of the world. There's a pointer to some elements and they have a size. That's the low level, that's what the hardware has. And we want to lift it up to somewhere where you could have range checking, where you can have copying of whole vectors, where you can vectors that can change size and all of this good stuff. And the key there is that you provide what's called a constructor that you can make a vector from, and a destructor that can clean up any mess you have made. That's the higher level. So this is the simplest example I know of for lifting a level of abstraction. And then you can start using it. There's a vector of doubles. I have parameterized my vector with an element type. The vector of double is some well-known constants, a vector of strings, some well-known language designers, and we can do more complicated things like a vector of pairs of strings and threads. The string is supposedly the name of the thread, and we initialize it with a couple of pairs of name and thread. they build the thread that should be there. And then we use it, and when we're finished, everything gets cleaned up recursively. So it cleans up the memory for the constants, it cleans up the strings and the memory for the characters, it cleans up the pairs and the strings and the characters and the strings and the threads with all of the system resources. So there's a key abstraction that we're using a lot in C++. It's for resource management, and it's one of the most popular types. And this shows an example of the onion principle. That is, we use layers of complexity to handle complexity. So we keep simple things simple at the first level, and when we want to do something more, get more control, we peel off a layer, we get more control, we have to write more code, our code gets more complex, and we keep doing so till we get to the hardware. And at each level of abstraction, you peel off, you cry a bit more. That's why I call it the onion principle. You make more mistakes, you have harder work to do. And the general approach to the design of C++ is what I think is an engineering approach. It's not pure math, it's principles and it's pragmatic, but you build something, you see what works and what doesn't, and then you fix it and you keep on doing it. And there's always trade-offs. I took some example from the aerospace industry. If every department optimized for their own ideals, you wouldn't get a decent plane. What you need is trade-offs, balancing of concerns. And you have to remember that the design decisions all the way down has consequences. It determines what kind of applications you can do well. If you have a balanced set of features, a balanced design, you can do lots of things. And basically, the value of a programming language is the quality of its applications. So I measure the quality and the value of what I'm doing in terms of what people are doing with it. And they actually, over the years, have been doing quite a lot of interesting things with C++. These pictures in my talk illustrate some of that. And that's the way I measure things. That's the way I look at it and feel that I'm doing something good. And if it doesn't work, I don't feel so happy. And we must work to get a better language so that you can do more of this good stuff. And the C++ community is thriving and it's growing. So some people think it works. We have about 4.5 million developers. There was a measurement 2 years ago by a survey, and that seems coherent with and consistent with what we've seen over the years. The community is growing, and basically C++ is everywhere. There's C++ on Mars, there's C++ on top of the mountains in Hawaii and things like that. And there's C++ in your pocket, assuming you're carrying a phone. What we're doing now uses a lot of C++ in the infrastructure that sends my voice and my image to you all over the world. And so we can look at another abstraction here in code. This is something we've been working with for a long time. It's generic programming. The idea is we can write algorithms, we can write code that works for every type for which it makes sense and executes optimally. That's both things are important. The usual C++ things you need to abstract, but you need to be able to afford the abstraction. And so here we first have a function, normal square root, but I parameterized it with a number, not with a type. So if I call it with an integer, it does an integer square root. If I call it with a double, a floating point number, it does a floating point square root. If I give it a complex number, 9 plus 9.9i, it does a complex double. And this works if and only if it makes sense. That is, number defines what it means to be a number. I could feed it a polynomial because you can add them and things like that, but the string 9 will not work. There is no way in the language as defined and as I defined number where 9 is a number. It's a string, it's a piece of text, and so that doesn't work. So it works for, the square root there works for anything that it thinks of as a number and not for the rest. Similar, a more common example is a sort function. The standard sort function takes a random access sortable thing, which is something that is a sequence of elements. It's something that has a sequence of elements, and that sequence has random access so that you can swap things around. And that's fine. And the things that are in it, the elements, you can compare using the less than operator. Now, I wanted 1, 2, but that also worked for lists. There's no random access, but I can go one after the other. It's got forward traversal, and it's easy enough to build. If I didn't have a smarter algorithm, I would just copy the thing that I wanted to sort into a vector, sort the vector, and copy it back again into the list. But I can define a forward sortable thing, and now I can call things. If I call it for a list, it says, do you have all the properties of a forward sortable? Yep. Do you have all the properties of a random access sortable? No. Therefore, you must pick the first one. So it does. For the vector, it decides quickly that it can handle the constraints on both of these, but decides that the stricter requirement of a random access sortable makes that a better choice than the less strict choice of forward iterator, forward sortable. So it calls that. And so I can now write code that not only works if and only if it has the right properties, the arguments have the right properties, but also can select the best algorithm based on the input. So that's how you get to the abstraction. And C++ is a living, evolving language. I started back in '79. We started a standard process, formal standard process under the ISO in 1990, and it took 8 years to get a standard. I didn't particularly want to standardize C++ then. I felt it wasn't finished, I wasn't ready, but they twisted my arm saying that you needed a stable language, you needed a language that wasn't controlled by some corporation that might compete with other corporations. This was an argument brought to me in my office by somebody from IBM and Sun and HP, and I wasn't ready, but they twisted my arm. They kept twisting my arm, so I ended up doing this. And we worked for almost 10 years, got one standard, worked for another 13 years, got another standard, decided that 12, 13 years is just far too long, and we're now shipping standards on a 3-yearly basis. We've shipped 14, 17, and 20 on time. This year is 20. We voted the standard in in Prague in February, and it'll become official when the standard has gone through the international votes and the processing in the ISO in Geneva and such. So we'll have an official standard in the fall. But interestingly enough, most of the features are already shipping in the major compilers. So if you want to try C++ 20, there's a lot of stuff on the web, and there's compilers to deal with it. And basically the aim, as far as I see it, is to improve C++ for building dependable and affordable software. That has always been the aim. That's still the aim. There are people who are into sort of language theories and such. I'm not. I'm interested in using whatever theories there are and whatever techniques there are to deliver dependable and affordable software. I don't want to hurt those little kids or anybody else. And so we have things that works in outer space or in your self-driving cars, or you have simple things like that coffee machine. A programmer is a machine for turning caffeine into code. Coffee machine is one of my most important tools. So we have things like that. And For looking at the future, I'm looking at Goethe's quote, "Dream no little dreams," and I would like tight and resource-safe C++ without any excuses and without any garbage collector, because that doesn't make the code predictable. And I still want it to be faster than anything else. That you get by looking at something called the core guidelines, which is something that a group of us are building, specifying our view of what modern C++ is and enforcing it by tools, so you can get tools that supports complete type and resource safe C++. They're not quite complete yet because it takes forever to get things done, but they're getting there. If you have Clang, you have some of it. If you have Microsoft, you have a little bit more of it. I hope GCC will get it soon. And of course, we need to be good on modern hardware, and that includes GPUs and FPGAs. Progress in that area, especially with the GPUs. There's a lot of good C++ for GPUs. And basically, since the purpose of the exercise is to work and use hardware well, it should be significantly better than alternatives. And we also want to speed up compilation and catch much more errors. C++ 20 has facilities for that. It has modules, so you don't have to go back to the old C model of includes again. If you could start from scratch, and then we have all the transition problems getting from here to there. And of course, we can quote Voltaire, "The best is the enemy of the good." We can't just do brilliant things. We have to get there. So we have to support change. We have to take concrete, practical steps, and we have to get benefits now, and we get it. And one thing that people sometimes forget when we talk about evolution and progress in the future is that stability is a feature. When people build something, they quite often build something that has to last for decades. And well, if the language changes incompatibly every 3 years, 5 years, 10 years, you lose the users. They can't, they simply cannot afford to change a language that often. So that's one place where the ISO standard has helped over the years to keep the language stable. I have code from 30 years ago that still runs. The operating systems and the editors and all of that changes much faster than the language. And basically, it took a lot of people to get to this point. And so I want to say thanks to the people in the standards committee and to the implementers and the library writers. There's a whole lot of people who takes part of this. The C++ community is large. The picture down there of the people cheering are the committee cheering after the C++ 11 standards. That was before we got we got about 3 times as many people in the committee now, and that's an advantage and a problem. And some of the people up there, like Dennis Ritchie and Christian Nygaard, are not from the committee. Neither is Alex Stefanov here, who's the father of C++ father of generic programming in C++. But the center of the C++ world is the standards committee. And that was roughly what I had planned to say. So maybe we should go back to the MCs a bit of a minute earlier, but